Hello everyone. My name is Tejal Lambore and today I am going to talk about distributed machine learning or DML. This is a critical area in the field of machine learning, especially given the growing size and complexity of datasets we deal with today. The main focus of this presentation will be on the motivation behind DML, the techniques involved, some of the challenges, and the application where it's used. By the end, I hope you'll have a solid understanding of why DML is so essential in modern machine learning and AI. Why do we need distributed machine learning? Traditional machine learning approaches are simply not efficient enough to handle the massive datasets we encounter in fields like healthcare, finance, and natural language processing. For example, training a large model on terabytes of data using a single machine would take an impractical amount of time and resources. Scalability is a major reason for DML. It allows us to manage enormous datasets and complex models by distributing the workload across multiple machines or nodes. Efficiency is also key. By splitting tasks across several nodes, DML accelerates the training process significantly. Resource utilization. Instead of relying on a single machine's resources, DML leverages the computing power of many machines, optimizing how we use hardware. Lastly, there's privacy. Federated learning, a subset of DML, enables model training without centralizing sensitive data, which is important in sectors like healthcare and finance, where privacy regulations are strict. One of the main techniques in DML is data parallelism, and it relies heavily on distributed stochastic gradient descent. This extends the classic SGD algorithm by distributing data across multiple nodes. Each node performs SGD on its local data, and then updates are synchronized periodically. Synchronous updates. In synchronous systems, all nodes have to synchronize after each iteration, ensuring consistency but potentially slowing down the process. This method is useful for scenarios where accuracy and consistency are critical. Asynchronous updates. Your nodes update the model independently. This leads to faster training since nodes don't have to wait for each other, but it can also lead to less accurate models. Federated learning. A great example of this approach is federated learning, where data remains on local devices and only model updates are shared with a central server. This is particularly useful for privacy sensitive applications. When the model itself is too large to fit into a single machine's memory, we use model parallelism. This technique splits the model into smaller sections, each running on different machine or GPU. For example, in partitioning, we divide the neural network into layers, each assigned to a different device. During the forward pass, activations are calculated by passing data through these partitions. Each device processes part of the model and sends intermediate result to the next device. The backward pass is similar, where gradients are computed and propagated back through the model. Devices need to communicate gradients between partitions, which introduces overhead and potential bottlenecks. This technique is essential when training models like deep learning architectures or large scale neural networks, which may have billions of parameters. Tensor parallelism is another technique that focuses on parallelizing operations within the model. Instead of splitting the model, we split large tensors, like matrices, and distribute their operations across devices. For example, in matrix multiplication, we split the matrix into smaller parts, each part being processed by different device. This reduces memory requirements and speeds up computation. However, this introduces communication overhead. Once each device has computed its parts of the operation, the results need to be combined, which can slow down the process if not optimized properly. To improve efficiency, we use methods like all reduce or all gather, which are collective communication algorithms that aggregate and synchronize results across devices. Choosing the right synchronization method is important for maintaining performance. Even though DML offers significant benefits, it also comes with several challenges. First, communication overhead. One of the biggest challenges is the constant communication between nodes. Every time data or gradients are exchanged, there's a delay, and this can become a bottleneck, especially with frequent updates. Second, load balancing. It's also important to ensure that workload is evenly distributed across all the nodes. If some nodes are working harder than others, the system becomes inefficient. Third, fault tolerance. Nodes in a distributed system can fail, and when this happens, the system needs to continue without losing progress. This requires careful design to ensure the system is resilient. Fourth, synchronization. Keeping the model consistent across multiple nodes is crucial. But this requires frequent synchronization, which adds to the communication overhead. Asynchronous system helps, but as mentioned earlier, they can reduce accuracy. One of the theoretical challenges in DML is proving the convergence of stochastic gradient descent algorithm, especially in distributed environments. Convergence refers to the model reaching an optimal or real optimal solution, and ensuring this happens in a distributed setup and not straightforward one. Data parallel SGD. Researchers analyze how SGD behaves in system where data is distributed across nodes. It's important to study the impact of different system properties on the convergence of SGD, particularly in non-convex deep learning models. Asynchronous communication. When updates are made asynchronously, it introduces variability in how quickly the system converges, and researchers are still investigating how this impacts the overall optimization process. Compressed communication. Techniques like quantization and sparsification, which reduce the size of the data sent between nodes, can also affect convergence. These techniques reduce communication overhead but can potentially lead to slower or less accurate convergence. Now let's talk about some real-world applications of DML. In healthcare, DML is used to train models for tasks like analyzing medical images, predicting patient outcomes, and even in genomics, where large datasets are processed to uncover insights into diseases. In finance, DML powers fraud detection system, risk assessments, and algorithmic training models. These applications rely on processing large volumes of data quickly and efficiently. Natural language processing (NLP) is another area where DML shines. Training large language models like GPT and BORT requires the power of distributed system to process huge datasets and complex models. In computer vision, tasks like object detection, image classification, and video analysis also benefit from DML, where models are trained on vast datasets across distributed nodes. When training large language models or LLMs, techniques like model and tensor parallelism are critical. These models, which can have billions of parameters, are too large to fit into a single model. Model parallelism splits the model across different nodes, and each node handles part of the computations. Tensor parallelism distributes tensor operations, such as matrix multiplication, across multiple devices to reduce memory load. However, challenges remain, particularly in managing the communication overhead between devices and ensuring effective load balancing so that no single device becomes a bottleneck. Looking ahead, there are several key areas where research is distributed in machine learning. First, efficiency. Finding ways to make communication more efficient, such as developing new protocols to reduce the time it takes to nodes for synchronization. Scalability. As datasets and models continue to grow, improving scalability will be crucial for ensuring that DML systems can handle future demands. Privacy. Federated learning and other privacy preserving techniques will continue to evolve, particularly in applications involving sensitive data. Researchers are working on ways to train models without compromising data security. Finally, exploring new model architectures that are specifically designed for distributed training will open up even more possibilities for large scale machine learning. And that concludes my presentation on distributed machine learning. As we have seen, DML is a powerful tool for addressing the growing demands of modern machine learning tasks, offering solutions for scalability, efficiency, and privacy. Thank you for your time.